Very much, Linning, and thank you also, Jim, for inviting me to this really great conference. It's been a lot of fun. And thank you all for staying until this very last talk. So I'll be talking about flexible material and mechanism design, and I'll start off by explaining what I mean by that. So typically when we make machines, we want things to be rigid, right? Of course, we're interested in mechanical motion, so we want the mechanical components to translate and rotate, but we don't want them to deform. So there are many applications that require such extreme stiffness, but it's kind of interesting to see that if we're looking at nature, that rigidity is actually something that is foreign to the living world, right? Actually, flexibility or compliance is essential for the robustness and efficiency of animals, plants, and of course humans. For example, like elastic tendons, ligaments, and muscles that allow the kangaroo to bound with great agility. And this Venus flytrap here actually captures its prey very rapidly thanks to organic bistable mechanisms. So many of these compliance strategies that we see in nature have been leveraged successfully for many different applications in design and engineering. For example, in architecture, we see elastic membranes, beams, and cables that combine into lightweight structures with great efficiency and also very pleasing aesthetics. These here are two rather famous examples from Frei Otto, the Munich Olympiastadium and the Mannheim Multihalle. Another area of application is robotics, where compliance enables biomimetic robots that have great capabilities. I'm not going to go into any detail here, but just to say that each of these custom designed and very laboriously designed examples are proof of concepts that flexibility, when done right, can be a strategic advantage that facilitates locomotion and greatly increases resilience to damage and ultimately failure. Now, this sounds great, so why are we not using compliance everywhere? Well, one reason for it is that when we're designing for flexibility, things get a lot more difficult than when we're relying on rigidity. So why is that? Well, first of all, we have to plan for large deformations. Whenever we get large deformations, we're probably looking at nonlinear mechanics, nonlinear material behavior, and all of these things add up to something that makes it just a lot more difficult to predict the equilibrium state of the systems or the equilibrium behavior. And unfortunately, while we have like simulation software and CAD software that can help us to test out some ideas, the real hard problems about designing for flexibility are still left to the designers. So it's like up to us to find the ingenious solutions. The software doesn't really help us. So for the last 8 years or so, this lack of design software was like a major motivation for my research, which sits somewhere at the intersection of computer graphics, digital manufacturing, and perhaps like computational mechanics. So the things that I'm interested and excited about are like how to facilitate the design of mechanical systems with some complex behavior, such as like mechanisms, robots, and also like structures that exhibit larger deformations, nonlinear membrane and thin shell structures, and nonlinear elastic metamaterials. So I'm going to talk about like 3 examples here today. Most of the things that you see here were actually done while I was still at Disney research. And maybe some of you know that Disney is not only famous for Mickey Mouse, but also for making like great robots, like which they call animatronic figures, and in particular robotic heads. So this here is one of the most recent additions to like Avatar Land and Walt Disney World. And what I think is really exciting about this robot is it's a test one. It doesn't have any locomotion skills, but the range of expressions in this robotic face, the nuances, and ultimately the believability of this performance are like unmatched compared to the competition. So it's also interesting to realize how many moving parts are necessary in order to get this performance, and how many hours of engineers, expert engineers, have gone into this design, because this is actually done, well, largely manually, let's say, based on a lot of experience, based on a lot of expertise. So the downside of this expert-driven approach is, of course, well, you have to have the experts, you have to pay them, and it takes time and money. So, well, that was like this insight of how difficult it is to make designs like this, that's what prompted us to look at alternative ways of making like mechanism design and mechanical design easier, faster, and ultimately more accessible to non-expert designers. So the first project in this line of work that we did is an interactive system where the user can bring in a virtual character, and our method then translates this virtual model into a 3D printable mechanical character. That system has a bunch of steps, but perhaps the most interesting one is a system where the user sketches a desired trajectory for the mechanism, and our system finds a mechanism from a database of template mechanisms that best approximates the desired trajectory. Now, how this works is, well, our system retrieves a set of examples from this library and then further optimizes the parameters of the mechanisms to best approximate the motion. And that's something that can actually, that's very fast. It runs at real-time rates such that you, as a non-expert user, can actually play around and quickly converge onto a design that works for you from an aesthetic point of view. So the second project in this line, we were thinking, well, can we go beyond like existing template mechanisms of like 4, 5, 6 bar linkages? Can we allow designers to like just take as input a kinematic chain that has a number of motors, and can we allow them to interactively decrease the degrees of freedom in this kinematic chains down to just one, like a 1 degree of freedom mechanism? So the idea of this is that the user in an interactive system, again, incrementally removes the motors, replaces these virtual motors that are like these red dots over here by rigid links, and such that incrementally you're getting down from 4 motors or something like that to a single degree of freedom linkage. And using this system, it's like comparatively easy to create rather complex linkages. Like this is a 10 and 111 bar linkage. There's like modeling the front and hind leg of a bull. And in this way, you can quite rapidly translate a digital animation into a physical design. So finally, the third project in this line that I was just going to quickly mention here, the aim is to enable interactive function-preserving editing of existing mechanisms. In this example here, the user was like shrinking down the bounding box of this Janssen linkage while preserving the functionality in terms of the trajectory of the feet, and then you can like go crazy and make your own Janssen walker with the funky linkage shapes. So taking together these tools, they add up into something that makes it overall relatively easy for non-expert users to create new mechanisms and machines. And for these custom designs, 3D printing is like the natural way of bringing them to reality. However, for these three things, we relied inherently on rigidity, right? And if we print them in the real world, we might find that actually some of these assumptions that we were making, they don't really apply, right? For links that are too long and too slender, they're not really going to be that rigid. They're going to be deforming. And the joints that we're using, they're also not ideal. There's going to be friction, there's going to be play, and all of these things add up to performance that might be pretty far away from what you thought you would be getting. Now, one way to mitigate these problems to some extent would be to take them into account during the design. But what if instead of like just trying to work around the limitations of rigidity, we just embrace flexibility and build it into the design tool from the ground up? And that's essentially the motivation for our work on designing compliant mechanisms, where the idea is simply that the user inputs a standard conventional mechanism, and we then replace the rigid joints with like compliant flexures, that is like blades, thin blades of elastic material that bend and twist in order to allow the mechanism to move. So the shape and the attachment points of these flexures are then optimized, they're like automatically, in order to give us like the performance that we want out of the mechanism, performance according to a number of design objectives that the user can specify. So how does this work, this design approach? Well, first we're starting like with a description, a parameterization of the mechanism. In this case here, we just have like the shape of the flexures that connect the individual rigid parts here, and then where they attached to those rigid components. So those are the parameters of the design. Once we decide on a specific design, we can do simulation in order to get the motion of that mechanism. And once we have the motion, we can evaluate various objectives. For example, like how well are we matching the trajectory that we wanted, or also like what are the deformations in the flexures, and are we happy with that? So all these performance goals, they're expressed by some objectives, which I just like call this function f of x. It could be anything. But well, I'm going to go into a little bit more detail on what objectives we're using in just a second. So this approach here, what I just outlined, you could call that the forward design approach, right? The user chooses some parameters, maybe does some simulation, builds a prototype, sees how it works, and, well, probably goes back to the start and iterates until hopefully they're happy at some point with the design. That is a seemingly simple approach, but it actually can be quite frustrating, especially if you're dealing with large nonlinear deformations. It's very difficult to anticipate what are the shapes of the flexures that best approximate the design objectives that I have. So a much easier approach compared to this forward design is to go the other way around, to say like, well, here are my objectives, go and find what are the parameters of the mechanism that give me the best performance according to those objectives, or said a little differently, what are the parameters that give rise to a simulated motion that optimizes all of these objectives. And that's what people typically call inverse design. It's the downside of it, I would say, is a little bit that it's technically requires a lot more sophistication. We need to do more derivatives, and we need to do optimization instead of simulation. But the advantage is that now the user can actually think in terms of high-level design goals, like really what is the performance that I want, and not what are the precise shapes of the flexures that I have to choose. All right, so the first and most fundamental ingredient for this inverse design approach is actually a way of simulating this behavior, right? We have to like somehow predict, like for a given set of parameters, what is the performance that we're getting out of it. One way of doing that is like, well, simulating the deformation of the flexures essentially would be to use like standard solid finite elements, and that's an approach that certainly works. The problem is just that this leads to very large problem sizes, and then we have large computation times, and well, things just take a very long time, and we don't really want that. So instead of doing that, we take an approach that directly models the nonlinearity and the slenderness of these flexures, and model them as discrete elastic rods, that is like piecewise linear curves that are augmented with an orientation field along the curve, allowing them to bend and twist. And that way we get away with a lot fewer degrees of freedom and still get pretty good accuracy. I'm going to show you some more details about that, but I think this is a good time to just underline that that's a method that's actually been developed within graphics by Bargu and Eitan Grinspan's lab. And it's something that has actually propagated beyond graphics, and it's used now a lot in physics and computational mechanics, so that's quite nice. All right, so with this simulation model in hand, what are the design objectives that we need in order to make a useful design tool? Well, the first one is probably that we want the mechanism to match a desired trajectory of some end effector. And that's something that is quite easy to formulate mathematically, and when we have that trajectory objective, we can optimize the flexures with respect to that objective, and that gives us a pretty good motion approximation in this case here when we do that. One problem that we have, however, in this case, is that while the optimization moves flexures around, we might run into intersections between the components. And quite obviously, when we would print that mechanism with intersections, that wouldn't really work out so well in practice. So we're making an additional design objective that asks for no intersections at all, strong penalization. And when we're using these two objectives together, then we get this performance here, which is still matching the trajectory quite well, but without any collisions. Now, these two things together give us a mechanism that is able to move without problems and tracks the motion very well, but in reality, we will find that, well, that's not enough to actually get a functioning mechanism, because the deformations in the flexures might be so high that they induce stresses beyond the yield threshold or the fracture threshold of the material, and then the mechanism is just going to break. So in order to prevent this as well, we're making another objective that penalizes the peak stresses across the entire motion cycle. And when we optimize for that again, we see that some of the flexures actually changed quite a bit. They got longer here, but now we can do the trajectory that we wanted. Maybe a little bit less accurately, but now the mechanism doesn't break anymore. And finally, the last objective that I wanted to mention here is like, unlike a conventional mechanism, we actually have to perform a finite amount of work to actuate this mechanism because we have to overcome the force and the flexures. And if we want to reduce the requirements on the motors as much as possible, then, well, we probably want to minimize like the peak torque for any given instant in time. And when we do that, you see that the performance at the bottom, the peak torques have been reduced by quite a bit. Now, that is probably a good time to say, like, this is not a free lunch, right? You can't have everything at the same time. In general, these different objectives, they will fight each other. So the designer has to make a call on like which objective is more important. They have to assign in weights that dictate the relative importance of these objectives. But this is something that, well, it's a high-level thing, right? It's like still very, very different than coming up with the flexure parameters that would give you this performance. So, all right, when you put all these things together, then you end up with a design tool that allows you to rather quickly and easily come up with a compliant mechanism, such as this one here. That's a miniature or a small-scale animatronic figure with like 2 compliant spatial mechanisms for the wings. Here's another example that indicates how compliance and digital manufacturing enable a new way of making really highly integrated functional devices without any rigidly moving parts. So that's a miniature mechanism for an eye. And when we try to make this eye mechanism using a conventional approach, like with rigid joints, the residual support material in the spherical joints, we couldn't get it out, and it made things so stiff that before the mechanism was able to move, the members, like the individual links, they deformed significantly and actually broke before we could actually move and use the mechanism. Here's another example that just indicates a little bit how this system could also be used for like compliant robotics or like or custom prosthetics. Yeah, there we go. All right, so in this case, we used computation and simulation in order to harness flexibility and to like make the design of like compliant mechanisms easy and robust and accessible to non-expert users. Now, if we go back to nature and ask ourselves, like, what are actually what's the source of the compliance, then we realize that very often what we observe as macroscopic elasticity is actually due to a microscopic network structure. And there are many examples of these network structures that give rise to really exceptional mechanical properties, for example, like muscle tissue or the cancellous structure, the trabecular structure of cancellous bone, or the vein structure of insect wings. So all these have really very appreciable properties. They're high performance, lightweight, and many other things. So nature certainly has its way of making these materials, but if we like use our conventional fabrication processes, then, well, these are rather ill-suited for making these kind of network materials. But thanks to like the now more and more available digital manufacturing technology, we're now able to make digital network materials that have like desired properties, right? We can make like elastic materials, elastic sheets, elastic solids. We can make precisely architected metal foams and lots of other things. Now, by changing the structure, the shape of the underlying microstructure, we can control the macroscopic mechanical properties. But the question is, like, how do we actually change the structure such to obtain desired macroscopic properties, right? That's the sort of the question that leads into metamaterial design, homogenization, and all these things. And these questions are, again, particularly difficult to answer when we're looking at large nonlinear deformations, like the ones that you see here on the bottom. So that the application that originally triggered our interest in this direction was 3D printed fashion, actually. This is an example from a fashion designer, Danit Pelek, who was looking at these 3D printed patterns that have like both very important aesthetic properties and at the same time they can have very, very different mechanical properties. So the question that we were asking was like, how can we understand the relation between patterns, like the aesthetics, and the mechanics that they induce? And in order to start studying these questions, we looked at the specific space of structures, so-called isohedral tilings. Now, isohedral tilings are like repetitions of polygonal shapes that are translated and rotated to fill the plane without gaps and overlaps. And what you see here are just like 6 of the, I think it's like 93 families of these structures. And what you can already see, I suppose, is that these 6 families span a pretty large visual range. Like in terms of aesthetics, the patterns that we get here are already very diverse, which is good for fashion applications, of course. And what turns out is that when we actually print these structures on a standard 3D printer, then we see that not only are these patterns like aesthetically diverse, but they also have very diverse mechanical properties that are characterized by strong nonlinearity and very high and highly anisotropic behavior. So how can we understand the space of these structures? How can we not only understand, but also communicate this material behavior in a way that's like easy to understand by maybe creative people that are not necessarily experts in engineering? So that was the goal of this project that I want to quickly talk about now. Our approach is essentially, you could call it a data-driven nonlinear homogenization approach, where we, first of all, for a given structure that we pick, we start by doing lots of native scale simulations that correspond to virtual tensile tests for different directions and different magnitudes. We then take all these simulation data and condense it into a data-driven homogenization model that's, in our case, based on Kirchhoff loft plates. And we do that for a large number of samples and collect all the data that we get from that in a way that allows like forward exploration of the material space, but also inverse material design at the same time. Okay, so in order to do this approach here, one thing that we need at the center is, of course, again, a simulation model. And in order to come up with a model, we first have to know what are actually the salient mechanical properties, what are the governing mechanics that we have to get right here. So one thing that's actually quite interesting to notice about these structures is that where they get their nonlinearity from. Initially, when we impose a deformation in a given direction, the structure responds to an imposed displacement just by rotating the edges, right? And this rotation is actually something, it's a little bit similar to a compliant mechanism. It doesn't cost us a lot, it's just bending deformation. But at some point, when we increase the deformation magnitude, well, that was not the right animation, but when we increase the deformation magnitude, then more and more edges will align with the direction of imposed deformation such that they eventually have to stretch. And when they stretch, then the stiffness is suddenly a lot higher than just for bending deformations. And that essentially explains the nonlinearity of the material, the transition between bending and stretching dominated regimes. And because the transition can be different depending on the direction, that then explains the anisotropy of the material. So what's a good simulation model for us to capture these effects in an efficient and yet accurate enough way? We certainly have to get like the nonlinearities right. We need to be able to model like buckling out of plane. That's very important. We need to be able to model like large bending and stretching deformations. And we again don't want to do that like with like the standard like sledgehammer solid finite element solution. We want to use again this reduced model based on discrete elastic rods that we extended in this case to work for network materials. And what you can see here, a little bit an indication, that's like a simulation, and well, visually it's sort of close to what you see in the picture, but I guess the data here speaks a little bit more for like the accuracy that we get out of it. Well, when a blue dot is close to a red dot, that's a good sign. So overall, we're getting pretty good accuracy out of this. And to make sure that this is not just a lucky coincidence, we started to like investigate this model a little bit more, compared it to ground truth finite element solutions, and it turns out that actually for some specific connection geometries, we are actually converging to the same displacement solution as like quadratic finite elements, and we can get very good accuracy at a fraction of the degrees of freedom than what we would need for finite elements. All right, so with this simulation again, how do we go about characterizing the material? Well, first of all, we need to cut out a swatch of that material. We have to isolate a representative cell. Once we've done that, we can probe that representative cell with a number of deformations that correspond to stretching in different directions. We do the same for bending, and that way, from these simulations, we get a lot of data that we then condense into this micromechanical model. That's a Kirchhoff-Loff plate. It has different components for stretching and bending, which are described by these material tensors C and B. And when we have these tensors, well, we don't just want to show them to the user, to the fashion designer. That wouldn't make a lot of sense. So we convert them into like these polar plots that quite concisely explain like what is the directional stiffness, what is the directional Poisson ratio, and what is the directional bending stiffness. We do that for different deformation magnitudes in order to get an idea of like how does the material change with increasing deformation, what's the nonlinearity that we get. And when we combine these things into the same plot for different materials, we actually get a pretty concise description of the material behavior. So we take all this data, we put it in a database, and then make these material browser that's sort of a front end that allows users to explore the space of material behavior in a structured way, like what's the maximum Poisson ratio, maximum Young's modulus. And if you want to play with it, there's like, you can access it even on your phone at structuredsheets.com and explore the space of these materials. Besides this forward exploration of the space, users can also do inverse design, where essentially they just have to come in and sketch a curve, like what is the behavior that we want of a given material. Our system finds like maybe the three most structures that are most close to this desired behavior, and then optimizes the structural parameters such as to best approximate the user prescribed target behavior. Well, you can see here that we're not exactly matching the target for these two cases here, but it's a pretty close match. And what's maybe more interesting is that if the designer has very concrete ideas about the mechanical performance, this gives them a choice of aesthetics that they can like choose from depending on the application. So it really enables this like joint exploration of like performance and aesthetics. So with this work, we were looking at this very particular space of isohedral tilings, which are arguably aesthetically pleasing, but our method could in principle be combined with any other material space that affords a continuous parameterization. However, just the fact that we have material, that we have structural parameters that we can scrub and continuously select different structure, that doesn't mean that we can change these parameters spatially to create, for example, spatially graded heterogeneous structures. That's actually something that's really difficult to do. That's a challenge not only in 2D but also for 3D materials. So that was the goal of this most recent work that we did in this context. That's going to be presented at SIGGRAPH this year, where we were actually trying to find a representation that would allow us to do just that, would allow us to create spatially graded heterogeneous structures in a simple and efficient way. Now, the approach that we're taking here is quite different from what I talked about before, where for the polygonal tilings, essentially you're figuring out here's a polygonal base shape and here's an algorithm for tiling. What we're doing here is we have a set of sites, and we're constructing the structure as the Voronoi diagram over these sites, but with rather exotic metrics. So how this works is that we take a regular grid, these dots here are just the nodes of that grid, and then we create a Voronoi diagram on top of this grid. If we use the standard flavor of Voronoi diagrams, then we would be using the standard L2 distance that tells us essentially like the Voronoi cell of a given site. Well, that's just the set of all the points that are closer to this site than to all other sites, right? That defines these typically honeycomb lattice structures that we all know. However, we're not actually forced to use this typical L2 disk-shaped isotropic metric. We can change the metric to other, perhaps really funky shapes that you see here. And then when we compute the Voronoi diagram based on these metrics here, we're getting very different cell shapes out of it. And not only are these interesting, visually speaking, I would say. They also give us pretty interesting mechanical properties that you can see here at Young's modulus. And these are all like relative values. It's not really a Young's modulus of 10 to the minus 5. It's just compared to a solid material, it's like almost 5 orders of magnitude softer. And you can also get very, very different Poisson ratios using this approach. Speaking of Poisson ratio, probably the most interesting, what we see a lot like in publications in material science are like negative Poisson ratio materials, like oxalic materials. And this plot here shows that our method actually captures a pretty interesting range of like strongly oxalic materials, like with values going up to -4. Actually, one of the structures that we can create using this method is this well-known reentrant shape that at least material scientists are very familiar with. But really, the big interesting part of this approach is that we can now go and interpolate between different metrics. We take any two pairs of metrics and we interpolate linearly between the metrics, and then we're asking the questions, what does that imply for the structure? What does it imply for the material properties? So that's what you see here. There's one metric on the left, one on the far right, and then we interpolate just the metrics in between and reconstruct the structure, the pattern, and measure the material properties that you get on the bottom. So what you can see is the structure is rather well behaved. It looks sort of beautiful. The material, the mechanical properties are also not so bad, but they're clearly not monotonic, right? You clearly don't get a simple linear interpolation or something like that between the two structures on the left and on the right. Well, it also doesn't need to always work out so well. Well, that's what's shown in this example here, where between 65 and 66% interpolation left and right, we're suddenly getting an abrupt change in network topology that induces a jump in the mechanical properties. So I'm not saying that this is a limitation of the method. It's just like if you're doing simple interpolation in the space and you're hoping to get simple mechanical interpolation, well, that's not going to happen. So that's something that would be interesting to look at in the future. Like how do you get like reasonably well-behaved interpolation of mechanical properties? And then, well, another, of course, application for this interpolation is that we can now create spatially varying continuous tilings. So here's just like a very short clip that illustrates some of these tilings that we made. Here's like an oxalic structure, negative Poisson ratio. Here is a heterogeneous structure that in the middle has a lower stiffness in this horizontal direction. And then here's another one that wants to bend out of plane because of the strongly oxalic behavior. How am I doing in terms of time? Bad. Oh, I guess that's a good sign. Well, I guess I'm going to rush through this, like, and trying to. We're doing well? I'm doing okay. Oh, good. All right, so these two examples of, like, compliant mechanisms and metamaterials, they sort of show how we can use, like, the geometry and the structure of the material in order to exploit flexibility, to control flexibility and to use that flexibility to our advantage. Now, if we go a step further and we adding something else into the picture, for example, pretangent, then we can also make structures that have the ability to transform built into the design. So that's something that some people here at least are very well familiar with. Some like to call that 4D printing. And one particular implementation of this 4D printing for self-deploying surfaces would be this approach here, where we're essentially just printing plastic tracks with a standard printer on a pre-stretched fabric. This is some like rather boring spandex material. And then if you cut out the model around the plastic tracks, then what you see is, well, if you make the network just right, then it deforms into a desired shape. So this idea is actually something that was previously explored by several people. Like we got inspired for this by like the Swiss designer Christophe Guberin, who was an artist in residence at MIT. So he did like a lot of like manual explorations, and it's a really complicated space to work in. And so we wanted to see, can we make a design tool, like again powered by simulation optimization, that would make this easier, like less guesswork, less prototyping, and a lot more in the virtual work. Now, besides like making butterflies out of this, like applications more serious, perhaps, that you could think of is like when you scale this process up or down, you could make like deployable tents, you could make foldable robots, ultralight gliders, or maybe even like foldable solar panels for space missions, who knows. But what all of these applications have in common, I would say, is that how do you come up with a structure that gives you the desired deployed state, the desired equilibrium state? That's a really difficult question. So what actually makes this so difficult? Well, there are essentially two reasons for that. One is, well, again, it's like large deformation, nonlinear mechanics, nonlinear material behavior. Humans are not very good at getting an intuition for that, right? But in this case, what's probably more important is that the design space for these things is actually very restricted. And to understand that, we can look at an analogy when we say like, well, this spandex sort of acts as a soap film that tries to minimize its area. Then we can use this analogy mathematically to say, well, then it's going to be something like a minimal surface. A minimal surface has zero mean curvature throughout, and that can only happen when the surface is either locally flat, which is pretty boring, or when it's saddle-shaped. It can't be convex, and it can't be concave. So the principal curvatures have to have opposite sign. So what are all the things that you can make up out of patches that have that satisfy this minimal surface constraint? Well, that's very difficult to know in advance. So given this restrictiveness of the design space, what sense does it make to aim for a fully automated solution where the user just says like, here's a shape, make it? So instead of doing that, we again took the approach where we were saying like, let's make a tool that puts the user in the loop, but let's try to automate the technical difficult design decisions as much as possible using simulation and optimization. It starts again with a computational model that's tailored for the application. It's again, like in this case, a discrete elastic rod network based on top of a finite elements for an orthotropic material, a membrane material. What's a little bit interesting to mention here maybe is that all of the design is parameterized just through the rod network. So when we move a point around here, the finite element mesh automatically adapts. And these things, along with a few other details that I'm not going to mention here, make it possible to actually do these simulations very rapidly, faster than real time, which then enables us to do design tools that have simulation in the loop without any noticeable lag. So one of these design operations is a simple forward design, right? The user just changes the topology here, adds a part here, then changes the shape, and observes on the right-hand side what's the corresponding equilibrium shape, the deployed state that I'm getting out of a given design operation. So that way you can explore a few things, but it's the same thing again. If you wanted to get to something specifically, it's very difficult to know what are the operations and parameter space that you need to do in order to get to where you want to be. So we for this reason, developed this inverse design tool where the user can just directly edit the equilibrium shape and select some points. We have some sort of a soft selection tool, and then they can displace and deform these selected regions. It feels like a forward modeling tool, but actually what's going on under the hood is that our method automatically computes the design parameters that make this change happen that the user wants to do, if it is possible at all. And it's not always possible, that has to be said there also. And for some situations, it can actually be very difficult to understand, to even know what are the things that we can actually do for a given design. So, and that's why we made this third component here, where around a given design, we analyze the structure of the design space, and we're showing the user what are the direction and parameter space that lead to the most significant change in equilibrium space? What are the changes in parameters that change the deployed state the most? So we illustrate the first principal mode, then we compute the second principal mode that's orthogonal to the first one, and that way the user can get an idea rather quickly of what are changes that I can easily do, and how can I combine them together in order to get closer to where I want to be. It's still nothing like an automatic tool, but with a little bit of patience and getting used to that interface, it actually becomes possible to make things like this that would be, for non-expert users, pretty much very, very difficult to do without a tool. So this is one example, the running example that I've been showing a lot. On the left-hand side, that's the simulated result, predicted by simulation, and then this is the result that we get out of from printing this design. they're pretty close, I would say, even though we measured material parameters, of course, but we didn't really calibrate things too carefully. So in general, this is a rather well-behaved design problem in the sense that, there's not a lot of sensitivity in the precise parameters, but again, it's difficult to come up with the exact shapes of the curves to get to this place without a tool. Here's another example that shows like a flower made of multiple pieces. Again, simulation is pretty close to the fabricated result. Here's a car or something like that. That's sort of a mask. I think that's pretty clear. And here, I think the original idea was to make like a samurai armor. It became a little bit of a different thing, but well, it shows some interesting designs as well. All right. So with that, I'm going to stop talking. I hope I could give you an idea that when you use compliance and you combine it with additive manufacturing, that opens a whole range of new interesting applications. And when you have the right design tool for it that uses simulation optimization, then those designs don't necessarily have to be more difficult than like a standard rigid design. And they can actually also be accessible to like non-expert users like you and me, I would say. So this is, of course, a result of the work of many, many people. I want to thank a few of the collaborators. Probably I'm forgetting most of them. And thank all of you for your attention. Thanks.